Yeah, so I'm here on behalf of Forerunner Research. So we're a company out in Eastern Canada. What we started to do is we produce auto chambers right now for PICARRO gas analyzers. So the one you guys would probably be most interested in is the N2O, methane, CO2, ammonia, and H2O analyzer, and that's a brand new one as of last year, I think. So we have the auto chambers, we have the multiplexer, and we have the full software to go along with all of this to do all your processing of your fluxes and all the fun calculations. But that's not actually, so this is the only business slide. So I'm also part of the core group at looking at the N2O chamber comparisons for INGOS. So this is work that we were doing this summer in Huittila up in Finland. And we have, so the whole point of it was basically, now we have all of these laser instruments that are coming online. They're these very precise lasers. So now we're able to address these questions that people have presented all day today about systematic errors in chamber measurements. And some of those are things like, how does the chamber fill up in different soil types? What's the best fitting function we can use for these chambers? So that was the point of the research at Huittila. Again, so there were a few aims in the campaign. We were looking at a variety of things like how does placing the chamber on the collar and placing the chamber in the soil affect your measurement? What happens if there's wind blowing across your chamber? What happens if you're sampling from your chamber with a syringe? The question of whether you have a vent tube or not a vent tube on your chamber. And then the other ones are leakage, either around the chamber, around the collar, or from the seals on the collar. And then the always present question of how are we affecting, when we put this chamber on the ground, how are we affecting the steady state concentration profile? So the way we were getting at this, and this has come up a few times this morning, is how do you generate a consistent flux of N2O so you can do these sorts of tests? So this is a device that's been used several times for CO2. This is the first time I think it's been done for N2O. So it's a 1.6 meter bucket basically with a big sand column on top. So we're able to pulse in nitrous oxide. We get up to about 1 ppm nitrous oxide in the bottom of the tank. And then we just watch that nitrous oxide decay out of the tank. And we're able to very precisely figure out what the flux is coming out of this device. And by doing that, we can put the chambers on the top, see what the chambers measure, reference them, and see what, sort of what of these factors are affecting chamber precision and accuracy. In this particular case, we're using for this experiment, 2 aerodyne lasers measuring N2O and 1 Lascaux laser measuring the N2O, all with about the same precision. So the first thing we did was, we want to make sure when we're doing this experiment, and sorry, this isn't really showing up that well. Some of the times we're placing 2 or 3 chambers on the soil at the same time. So the first thing we did was a bunch of theoretical work, making sure the chambers won't interact with each other, won't disturb each other when we're doing the experiment. And that's, unfortunately, this is not the sexiest plot I've ever made, but this is just showing 2 chambers on the soil, and basically in our system there's no interaction between the chambers, which is, fantastic because we don't want that to happen. So the campaign was 22 non-steady state flow-through chambers. We have 1 hertz data from the chambers themselves, from the sand below the chambers, and from the reservoir that we're injecting into. The chamber sizes were ranging in volume from about 0.003 meters cubed to 0.38. They were all different shapes and sizes. Some of them had fans inside them to mix the chamber. Some of them had vent tubes, some of them didn't. So we were testing the effect of wind speed, wind direction, the vent tube, any sort of headspace mixing. So these are the fans with and or the chambers with and without fans. The effect of collar insertion, the effect of chamber leakage, and also the effect, like I was saying, of manual samples on these chambers. So this is just a nice slide showing all of the various shapes and sizes of chambers. So they range from, sort of arm span sized chambers to chambers that were sort of this big around. And you can see a few examples of us testing chambers side by side. We also have the very, very tall chamber over there. So we have a good sample of various chambers, even some made from wooden boxes. So again, what we did was we injected this tank with 1,000 ppb, that should say ppb, sorry, of N2O. We did this is the protocol. So we did 3 replicates without wind, 3 replicates with wind, and we repeated that twice to get enough data for our statistics. We did a leak test, and then we did a whole bunch of special side tests, which include the manual sampling tests. So these chambers, all of them, regardless of size or shape, were closed for 10 minutes. And then between samples, we had a 20-minute stabilization time to let the soil sort of go back to normal. And the fluxes we were looking at vary between 20 and 120 micrograms of nitrogen per meter square per hour. So this is again preliminary data right now. This is how all of the chambers compared across the campaign. So the closer to 1 you get, the closer the chamber is to measuring the true flux coming out of this system. So just a few things to point out here. We were fitting it with 2 functions, a linear function and an exponential function, to try to get some of that curvature that was talked about this morning. The 2 or 3 things that I want to point out in this slide are there were some interesting results in this campaign in that usually your linear function underestimates your flux. A few of the chambers we were playing around with, the linear flux actually tended to overestimate compared to the exponential functions, which were not really, again, preliminary data, not really sure why that's happening. There was a significant effect of headspace mixing. So in this block here, you can see an example of a chamber without a fan, which is number 15, so one that's probably stagnant inside the chamber, and one with a fan, which is 16. And the 2 things that I want to point out there are the size of the error bars, first of all, when you're not mixing your chamber. We got quite variable results, and we tend to get closer to 1, basically, if we're mixing the chambers. The last one we're not really sure about, but it's an interesting result. So this is number 22 on the slide, is that very, very tall chamber we were showing. So it was about probably 1 meter tall, sitting on the top of there, and that was severely underestimating the flux, which was a surprise and possibly due also to mixing. So these results will be, well, I'll tell you guys in a bit, actually. So there's some of the cooler stuff is what's actually happening when you're putting this chamber on the soil. So since we were measuring in the sand column, we're able to see what's the chamber placement, what the effective chamber placement is. So you're seeing here 2 different chambers, one that has a water seal and the other one that doesn't have a collar and is just pushed directly into the ground. The blue line is the chamber increase in concentration over time. What you're seeing is in the green line is the soil concentration. So what we're actually getting when we're putting the chambers on the ground is a piston effect, where the chamber is forcing atmospheric air into the soil profile. And that actually leads, I mean, in this plot, for example, we're getting a 50 ppb change in the soil profile over a 10-minute closure. So we're underestimating the fluxes by quite a lot when we're doing this sort of thing with the chambers. So I guess I didn't throw in the other slide. The same thing on the flip side, when you end up with a chamber that you're not doing a lot of piston action with, so if it's just sitting on the top of a collar, you're not getting this disturbance. So there is a significant impact of how you're actually deploying your chambers in the field in terms of what the fluxes you're getting out of them are. So this is another really interesting plot, and it's just, so again, the soil concentrations and the chamber concentrations, but this is when we're manually sampling them. So we're taking 30 mil syringe samples from these chambers, and you can see very clearly every time we take a 30 mil syringe sample, we're disturbing the soil profile quite drastically in some circumstances, just because we're creating an underpressure in the chamber and it's sucking CO2 up through this, or I keep saying CO2. I did CO2 stuff for a long time. Sucking N2O up through the soil profile. So yeah, so this is, like I said, is INGOS. This is all stuff that's going through Helsinki and Thunen Institute, and it should be published in, well, hopefully the first paper published next year sometime, and the second paper that has all the experimental results shortly after that. So I guess I just wanted to give you guys the heads up that we're doing this and to look out for the papers. And if you guys have any questions, I guess, are we taking a break right now, or?
Yeah, we have time for a couple questions.
Okay.
And then we'll be taking a break.
Yeah, really interesting stuff there. On the on the disturbance effect that you talked about last,
Yeah.
I'm just wondering if the vent tube presence or absence of a vent tube had an effect on that.
Yeah, it did. So in general, with the vent tubes, you had less disturbance when you were sucking a sample out, by about half. So the vent tube didn't take care of all of the disturbance in the soil profile.
And how about the placement effect? Did it affect that?
Yeah, so there were various placement effects with various vent tubes, but once again, the vent tube didn't take care of the whole placement effect. 90% of the bad placement chambers were ones that were piston-sealed around the outside of the collar, so that were pushed onto the collar instead of placed or seated like a face seal onto the collar. So you're getting that piston action of the gas going into and out of the soil profile.
And also in your design, you had you filled the chamber to the bottom vessel to a fixed concentration and let that decay.
Yeah, exactly.
Right? So in theory, the flux is decreasing during that time, or was it negligible?
Yeah, the size, the volume of that container means that the flux was decreasing very slowly. So it took us 3 days to get through that full range of fluxes. So we would get within a few micrograms per meter square per hour, and we would be able to maintain that for several hours.
But so during the period the chamber was on there, you consider that a constant flux?
The fluxes are more or less stable, and we're able to measure them as well, so we can see if they're dropping off over that time period.
Yeah, really interesting.
Can we send you different chambers you could test?
So unfortunately, the campaign was this summer. Yeah, they solicited to get chambers from a whole bunch of different places. Most of them came from Europe. There were a few, it was us and Lycor that were over there from North America. But it's certainly, you can talk to the people at Helsinki. They still have the giant bucket there, so.
Okay, thanks.
Before I get there, I was wondering about the soil type. It was sand, and that made me think of if soil type could have, texture could have an influence.
Oh,
and then it led me to how much water was in the sand itself.
Yeah, so the sand in this particular instance was totally dry. We were trying with 2 different types of sand, so we had a fine grain and a coarse grain sand. But when you're doing this sort of, the very controlled experiments, you start throwing in different soil types, and you're probably getting nitrous oxide production unless you sterilize them first. And so we tried to keep it as simple as possible to try to show whether or not the chambers were working, but certainly soil texture has an effect.
So some of the piston effects would be because of the texture and
of the sand, yeah.
In your test where you took sample out and found an effect, what proportion of the headspace volume was your sample?
It varied between chambers, obviously, because there was quite a range of volumes. But I mean, in the examples that I've been showing there, this is a Thunen chamber, so it's probably like a meter by a meter by a meter, so quite a big chamber.
Right.
And it was still, we were able to see the effects in the soil profile of 5 ppb per sample draw.
But how big was your sample then?
30 mils.
Oh, okay.
So tiny compared to the size of the chamber, basically, but.
Okay. I mean, that's one of the things that because we evacuate the vials, that means we don't have to take such a big sample. When the vial is not pre-evacuated, you have to flush it, so you've got to take at least 3 times the volume of your vial.
Yep.
But if you take a small, but even 30 mils is quite small to have
so
such an effect. So
I would imagine it would be proportionate. So like 30 mils here and 5 ppb shift, I would imagine if you went to a 12 mil vial, it would be more like 2.5 ppb.
Yeah.
So you're probably proportional to the amount of air you're drawing.
Okay, thank you. One more question.
I just had a question about wind, which was one of the effects you said you looked at.
Yep.
Did wind have a thing, and orientation of the vent tube exit compared to the wind?
Yeah, so I mean, It really depended on the chamber. So the biggest thing that we saw was chambers that were rectangular or square. When the wind hits a square face and it stops in its tracks, that causes some problems with, depending on which way the vent tube is oriented, obviously on that square chamber, but you can get under pressure or over pressure on the front side of the chamber and under pressure on the back side because of that wind. Basically, think of a wind tunnel throwing a car in there, but it's the same effect with the chamber. So yeah, we did see significant wind effects and wind effects that changed with the orientation of the vent tubes. And they tended to be worse, like I said, on the square or the rectangular chambers than they were on the circular ones, which I guess just are more, better for flow.
Was it better to have the vent tube sideways to the wind?
It was, it changed with chamber, basically. It was, and it depended on so if some people had their vent tubes oriented up, some were tucked in to like a little tube on the side, so it would depend on which way the vent tube was facing to, or whether it was shrouded or, covered from the wind. So there were, a lot of variable results depending on the chamber design. It's certainly the worst one that we saw was a vent tube sticking straight up and the wind coming across it, because it just sucks N2O out.
Thank you.
Yeah, no problem. Thanks, guys.